see, sharing. Let me start by going back to our third slide. And this slide was sort of setting the path in the forest. So we have spent time mostly doing the yellow highlighted part. This is rigorous Hamiltonian-based approach to study dynamics of systems. And we are not done with it, but we are getting closer to done with it. And in the same brush stroke, we have also certainly touched upon the Langevin equation being a stochastic limit of the theory that we have developed. We haven't really done the Langevin equation stochastics calculations, but I may skip that because it is relatively straightforward and it's in Balakrishnan's book also and in other places. So it's very commonly available in all books. But anyway, we'll see. What I will do next, maybe not today, but next, would be the sort of like a master equation development. So basically, it is description of the dynamics of stochastic systems, meaning randomly varying systems. Now, so it is obviously quite different from what we have done about rigorous dynamics. But also it is very important. Why is it very important? It's very important because suppose you want to study the behavior of the stock market. Is the stock market a stochastic system? No, it is not a stochastic system. The stock market has very distinct memory. There are various laws of how the stock market behaves. Stock market has, for example, strong correlations. For example, if you have gold price going up, it almost always means that other prices that are more tied to the stability of the economy, like banks and so on and so forth, may actually be on a downward slide. So it's not a stochastic system, but in a certain window, it might behave as a stochastic system. And so there is a great need for studying the stock market from the perspective of a stochastic system. It's just an example. There are quite a few things that we have going on that we encounter in our lives that fall under this basket of stochastic systems. So therefore, I think it is a good idea to learn a little bit about stochastic systems, not really do it at great depth, but kind of touch upon it, be in a position to use this kind of approach as an approach of choice. For example, you can imagine, signals can be quite random, depends upon where it comes from. If you're looking to signals from the Milky Way galaxy, which is our very own galaxy that we receive, there is a great deal of randomness in it because there is an enormous number of emitters. And each of these emitters are emitting electromagnetic waves that we receive. And there is a great deal of stochasticity in there. That said, there is also a lot of systematic behavior that we see. But you need to subtract off the stochastic behavior a lot of times to be able to capture the systematic behavior because it is below the noise or at the noise level. One example of where that has become immediate in the recent past relatively highly relevant is this Vera Rubin telescope, which has gone up and which is not gone up. It's actually in Chile. It's a ground-based telescope. But Vera Rubin telescope gives us thousands and thousands of times better quality images than the Hubble and the James Webb, the two telescopes which are actually in space. It also covers a much wider, swath of the sky. Now, why is that? It's ground-based. It's sitting uh, on the Atacama Mountains of Chile, and therefore, it is subject to atmospheric noise, although the altitude is high. The answer is very simple. The answer is yes, it has a fantastic lens which allows it to have incredible swath, but it also equipped with an extremely high-tech noise cleaning setup. And it is that noise cleaning setup that kicks in every time an observation is being recorded. And therefore, in real time, or with slight processing, you can get images that you simply cannot get in James Webb or in Hubble. Okay, so this is another case where the noise is a real random background noise that is being removed, um, thereby giving you high resolution. So there is a real need for studying the stochastic systems and their dynamics, and I'll do a little bit of that. Uh, kind of that's next on the menu. And along with this, I'll also probably give a couple of lectures on the diffusion equation, because the diffusion equation also plays an important role. So for example, suppose you have an oil spill. How will this oil spill move, let's say, on the surface of a sea or ocean or what have you? You can't study the system using exact dynamics. I mean, you're going to go absolutely crazy doing it. There's no computer in the world that'll get you even close to it. Nor do you want to do it that way, but you want to do it probably by setting up a diffusion equation, by plugging in the properties of the diffusion equation and doing a relatively straightforward mean field calculation to get you to the estimated answer. And your answer will be more or less in the right ballpark to do some engineering of some kind of an oil cleanup, or whatever it may be, garbage patch. You can imagine this as an example. So there is a great deal of need for doing that kind of dynamics, and it's scientists like us who end up doing it. And so there is therefore a good necessity for it. One of the things that I'll do, um, since we'll be finishing the discussion here with the discussion we started of the harmonic oscillator system, I'll use it as a sort of um, pathway, if you will, to take you to the study of the second circle here, which is nonlinear equations and integrable systems. I will get into this area in April. That's what I have in mind. This area is for April. The stochastic part of it is really for hopefully between Thursday and the following week, and maybe a little bit longer if need be. But this area, I'll get into it in April because there's a lot to discuss. And I think the area is very promising and also very important because you want to study ocean currents, well, you'll end up with nonlinear equations. You want to study ship design, you'll end up with this kind of nonlinear equations. You do anything, you want to design a park for kids and you have a water channel, you're going to end up doing nonlinear equations. So it's that common, and it's also in principle exact. It's not like something noisy. So therefore, we will cover these three areas. the rigorous one, then the master equation, diffusion equation piece, and then this nonlinear equation piece. Thus to give you a sort of a map with its own little, uh, dive-ins of what you get out of it. That's the best I can do because these are the fields I'm either quite familiar with or somewhat familiar with. And as you have seen already in the spin studies, each of these fields are so detailed that unless you have actually worked on them, you really cannot do very much by going through a course like this. And that is the only reason why I've been trying to take you to the actual model calculation such that you have some first-hand exposure to how this is done. So anyway, so that's sort of what I wanted to point out and cover. And now I'm going to move on to where we kind of were, so you don't feel too lost.
I guess after 80.
After 80, yes. But I want to start a little bit behind so we can, because what we are doing now is unfortunately a little bit messy. So this was what we talked about. This is how we began the harmonic oscillator problem using normal modes. And then the point I made was that the moment you bring in any kind of impurity, this normal mode approach begins to become difficult to use. It's not that it's impossible to use, but it's difficult to use. In fact, that Ullersma study that I mentioned in 1966, where he got the physics right, Ullersma did use a normal mode approach, but he managed to finesse and work with it in such a way that he could treat an impurity quite correctly. And we discussed the derivation of the diffusion coefficient. We'll come back to diffusion equation later on. And this is where we had started our journey into something which is deeply more researchy. It's relatively recently developing studies of harmonic oscillator systems with all kinds of decoration, like impurity, like two kinds of masses, multiple kinds of masses, still in one dimension. With periodic boundary condition, though, although that is not a showstopper. And we discussed the main results. And this was the discussion of the main results, where we talked about the 2-particle, 4-particle, 6-particle, 8-particle type systems, ultimately going to infinite size systems. So periodic boundary does not matter. If n goes to infinity, you never really finish the loop. So periodic boundary issue goes away. And for a single impurity system, you end up getting not for sorry for a pristine system, you end up getting a pattern of deltas, like 2 times a constant, and the rest everything else is 1. And then when it closes up, it's a 2. So if it's infinite, this you never get to this 2. You keep on getting the ones, the 2, 1, 1, 1, 1, 1 forever. And then if you have like here, and then if you have a single impurity, then you have this 2 lambda 1 1 1 1 1 1 all the way to 2. And here also, if you have n going to infinity, it's 2 lambda and everything else is 1. So anyway, so that's the pattern, and this kind of a series of deltas results in a continued fraction that's summable. And that summable continued fraction is this one. This is a single impurity problem. And inverse Laplace transform gives you to an A0 of t, or a relaxation function that has this form. And this is how it looks like, as we discussed. And if you look at it with the impurity mass becoming heavier, then it begins to look more like an exponential decay, although it is not an exponential decay, but it begins to look more like it. And that is primarily because of the conspiracy of the mathematics here. And this was associated with the stochastic decay mistakenly, and it's not so. So we made this point. And just to remind you that what is going on here, if you look at it with great precision, then you actually see a decay like this, and which is very far from an exponential decay. And this was the discussion that I had, I think, about a week ago. And then we came to this Professor Yu's work, where there was an 8-particle system with 3 species of masses. There's an M1, M2, small and heavy, and then there is an impurity M0. And then the problem was, how do you solve this problem or any kind of version of this problem, which may be even more complicated with more different kinds of masses and multiple impurities and what have you. Is there a systematic way to solve that problem? And the story that we have been discussing is there is no really good systematic way to solve such problems. And the fundamental question can be asked, why would you even want to worry about the problem? Right? I mean, why is it important? Well, that question is in my own opinion, a very important question. But at the same time, that question sometimes is not all that relevant when it comes to very basic systems. We do very basic systems in part because it gives us insights that we use for more realistic systems. But if you don't have that insight, then doing the more realistic system becomes darn near impossible. So when you are given a problem in real life, suppose you yourself are a researcher, you are a professor, you are trying to solve a certain problem, and this problem, let's say, is widely used in, say, geology or someplace, then as a physicist, somebody who is, let's say, a theoretician, you will be hard pressed to dive into the real problem because you will not be able to do it. So what do? We build layers of simpler problems. And it's a layer of simpler problems that allows us to develop enough insights, enough trickery to crack the bigger problem. So this is a problem which is in that layer. That is a must-do layer. And that's why it's important. That's why I chose to do it. In fact, I don't know of anyone who does it in any class like this. So again, this problem has produced not only this gentleman, Professor Yu's career, or later career, it has certainly produced a couple of PhDs also, various versions of it. But this particular problem that I'm describing to you is actually the sum total of all of that, and directly from Yu's own notes, and then whatever I've constructed, because Yu wasn't able to share all his work with me. I mean, he and I lost touch for about 25 years in between. So that's how things were. And he's an elderly man who hardly uses a computer, so it's like that. Anyway, so if you write up the potential, it looks like this, as you saw, and the kinetic energy is that. And so you can construct the Liouville operator from the Poisson bracket, and you can calculate the F's from this Liouville operator. And this is the detailed structure that we described. And if you write down the F's have this kind of a look where the first F0 is P0 for a two-particle system. This is F1, this is F2. This is F0, F1, F2, F3, F4. F5, I mean, F0, F1, F2, F3, F4. Yeah, so 5 Fs and so on. So we discussed this. So again, no problem here. Then, of course, if it's an enormous amount of work now to the next level of calculating the length squares of the Fs. And then if you organize them after years and years of work, he ended up finding this beautiful triangular pattern. And then when you look at the deltas, of course, you'll get the same kind of pattern with the numbers slightly being different. And here you see that same pattern emerging. For example, if you look at the 10 particle chain, you have 2, 1, 1, 1, 1, 1, 1, 1, 1, and back again to 2. The same pattern that I showed you of this 2, 1, 1, 1, 1, 2, 2. And if you open it up and n goes to infinity, then these ones continue forever, right? That's what we have seen. In this case, the impurity mass is captured through this parameter lambda, so that's what this lambda is all about. And we have seen this. So question is, how do you get it? How do you get this material? And this is kind of where we have been trying to develop some kind of an understanding without getting our hands too wet. So And again, I just want to emphasize that these calculations are really difficult. Now, what does the word really difficult mean? Really difficult means a couple of things. Really difficult means that sometimes they're very specialized. So there are certain tricks, there are certain identities, there are certain methodologies that you probably should know to make the calculations easier. Are they unique? Probably not. Very few things are unique in physics. Okay, there are multiple ways of going to the problem. So, but this is, you got to do the calculations that I pointed out, so you have to do it. Partition function calculation itself is relatively straightforward because these are all Gaussian integrals at the end of the day, because the interaction is quadratic in nature. So the interaction is Gaussian, and the kinetic part is trivial because it is just momentum square over 2m. So it's a very simple one. So let's not waste time on it. You just simply figure out that these are the factors which come, and you punch in the factors. Depending upon the number of different types of integrals, this power of the factors enter, and that's basically that. Now, the harder part comes more with the potential energy part. And again, potential energy part has one very nice silver lining, that after all our integrations are Gaussian integrations. Hard problem is you have prefactors with the Gaussian integration. That's the hard part. But even for Gaussian integrations, when you have nesting, right, you have interaction. So therefore, the integrals are nested. They're interlinked. So untangling these integrals is not trivial. So even for a partition function calculation, just because you have interaction, untangling it is not easy. And this is where the first of these tricks that I showed you came in, that you had developed. And he basically took the interaction between, let me bring it down, interaction between x1 and x2 and x1 and x3. And they are characterized by A and B. Of course, it's a spring, so these are spring constants. And then it turns out that if you can eliminate x1, so remove one of these degrees of freedom, you get an effective interaction between x2 and x3. And this renormalization, if you call it renormalization, involves this integral here. And the result of this integral is this quantity here. So therefore, this is the prefactor, and this AB over A plus B is the renormalization. So in other words, suppose A and B are equal, they're both equal to 1. So then AB over A plus B is going to be half. So the strength of interaction between x2 and x3 by elimination of x1, or rather by integration over x1, becomes half strength. Every time you go through an elimination, you import a factor of half. That is the point. So once you have derived this trickery or this step, then you don't need to calculate. Whenever you encounter this kind of integral, you can just directly do it without actually hard work. And this is exactly what we discussed from U-sketch. You have this 8 particle system. Is it? Yeah, 8 particle system. And in this 8 particle system, the way he does it also illustrates how cleverly you can do it. He basically replaces all the M1s in this case by essentially drawing these out. So then, he replaces all the dark masses here, and then he has this. Um, I don't know why he has made this dark. Anyway, this is not dark. This is just a regular mass. So now he goes through another elimination where he eliminates this fellow here. Then he eliminates, oh, I see, that's the thing he is doing. Whatever he wants to eliminate, he has blobbed it up here. So this is eliminated, then you have that. And then turns out that if you go through all these eliminations, this becomes A over 6, this becomes B over 2. And if A and B are the same, then you wind up something which is 4 in this case. And if A and B, okay, this one is coming from these eliminations, and the final one is this version here. Anyway, so the point is that he has removed 8 bonds, and he imports a power of 7/2. This, of course, is the last integral that will generate an infinity. So he puts in a V there. I think there's an a square root of 2ab plus 3b. If b is same as a, you can do the math. It's very simple. So this is the kind of way he's renormalizing. And then you can actually do this step by step, which is what I have tried to show, and get the very same result. This is something we have discussed. Okay. And this is the final result. You can do it step by step instead of the diagrammatic. Obviously, diagrammatic way becomes very, very powerful once you can use it correctly. All right. We have done this pretty much. Now let us get to the calculation of the f's, because the f's and the length squares of f's, norms of f's. Here, it has been denoted by square, actually. It is not my choice. This is what our AI system that I was using to convert the equations to typed equations was doing. And after a while, I gave up because a few times I tried to correct it and then it kept on ignoring me. So I said, okay, screw it. But it means the same thing. Norm of F1 and norm of F1. Actually, this is the correct notation, but historically it's been norm of F1, which means F1 square ensemble average. Here it's done as norm square. But basically what this is scalar product of F1, F1. That's what it is. So anyway, F1 squared then ends up being this quantity here and e to the minus beta v. And now you can already see that there are entangled integrals entering the picture. So this is what I was saying. If you go back here, I was saying that this is not trivial because the entangled integrals come in. And so this is where some hard work is needed. And this is the hard work that here we are referring to. This is the simplest of the hard works. Now, this equation can be fortunately done, and okay, so this is the piece here, and hasn't really been shown clearly, but this is the answer that you get. You can actually do it online using Wolfram, or you can do it by hand. It can be done. Anyway, so ultimately you get an F1 mod square, you get a delta 1. Similarly, you can go to F2. F2 is very simple because it involves the moment operator. And here you get this piece along with that. Can be done directly. And then F2 squared is very simple. Then you get to F3. And as you can see, F3 involves these 4 characters, x2, x minus 2, x1, and x minus 1 is in F3. So now when you make the norm of F3, you'll actually have to have this thing a square before the Gaussian for the integration. Because if you look at it, this is what I mean. So this whole integral will enter. These are going to be easier, but this is going to require a little bit of care. So this integral can be done, and so the pieces that can be easily done are here. And then the J piece is the one that has been separated out, and that has this factor. So it's a J integral. So one of the things that I want to point out here, which is where I'm heading to, is how do you deal with these guys? Okay. Is there a systematic way of dealing with them? Answer is yes, there is. There is a systematic way of dealing with these integrals. And when you deal with this particular integral, in this case, how it is dealt with is not shown, then you get this result. And the way it is done is by using a formula where x1 minus x2 and x minus 2 and x minus 1, these are here, and x2 and x minus 2 and x1 and x minus 1, they have these factors m and n, and this m and n have specific values here obtained through the kind of reduction I showed you. And in doing that, there is this formula that is available in the market. You can use this formula and get the result. Okay. Where does this formula come from? So I wanted to have a little bit of conversation on that. Yeah. So this formula has actually been done in many places. It's more of a mathematician's trick rather than a physicist's trick. So essentially, the hard way of doing it, or the quote unquote better way, if you will, from a mathematical point of view, is you do a coordinate transformation. So you define u1 as x1, u2 as the bond, x2 minus x1, u3 as x3 minus x2, u4 as x4 minus x3. Observe how it has been structured here. x2 minus x1, x3 minus x2, x4 minus x3. So there is no plus 1 minus 1 design that we are using. It is just genetically set up for 4. And then x2 minus x1 plus x3 minus x4 is the minus sign and the plus sign alignment. That's how it's designed. Of course, you can switch them. So you have these 4 U's. And with these 4 U's, you can rewrite the x1, x2, x3, x4 in terms of the U's. So x1 is u1. x2, you just add these two. So x2, u1 plus u2. Similarly, x3 is u1 plus u2 plus u3, and x4 is 4. Okay, nothing that bad. And then the prefactor, the term x1 minus x4, this last term ends up being this term. Jacobian is 1. And the prefactor here, this prefactor ends up being u2 minus u4 squared. So this becomes your setup before we apply the formula-based solution. So this is how the formula works. You basically take this U column matrix or row matrix, U transpose and you construct this operator, this matrix A, to rewrite the exponential, to rewrite the argument of the exponential. So it is U transpose AU, where A has this structure. So you see this structure has the M and the N here. Diagonal has 1 plus M, N plus M, 1 plus M, and everything else is M. Where was this M and N? Here is your N, here is your M. Okay. So if M is 1, N is 1, fine. Then the matrix is just a little simpler, which is mostly our case. And then if you actually can see the mathematical formula that's there, and the formula is that the prefactor is also written as U transpose, but another matrix MU. And this is the structure of M. So I have to do some more investigation, by the way, on this particular one, because I want to see what's in Gradstein and Rizek. And I confess I haven't done that yet. Probably they have something similar going on, but this matrix thing was very intriguing to me because I thought that was quite cool. Anyway, the point is that you have to find the trace of MA inverse, that is the final answer, along with this 1 upon 2a factor of basically this integral. By the way, this k is 3 because we actually have a triple integral. We are integrating over 4, but one of them, if integrated, will give us an infinity. So we actually have 3 real integrals that we are doing. And that's the reason why you have D3U. And the U vector is U1, sorry, U2, U3, and U4. So this is U2, U3, U4. And this is also U2, U3, U4. This is the transpose of it, of course. And then the final answer really is this and then that factor. And the trace term ends up being this, having a structure like this. And if you now put everything together, you find the determinant of A, which enters here. Oh, what did I do? Determinant of A enters here in the denominator. So determinant of A is needed. A to the 3, pi to the 3, everything is square rooted. And then MA inverse. M is this, MA inverse is this. So step by step, you have to go through this whole gig. And if you do that, then actually all these integrals can become quite manageable. I don't believe you use this formula. I believe he invented the renormalization approach to make it very physical. And he did it that way mostly, not everywhere, but mostly the ones I have seen. And then you can actually work it out and put it together, and you get the very same result as you did, which is this result here. So to get that result, there are a couple of different ways. I showed you one way. Well, I didn't show you. I just showed that renormalization approach is what you used. But there is also this way. And as a result, you can actually do these integrals without going completely bonkers every step of the way, because there is a method to the madness. Now, whether this can be applied or whether this kind of works for something which are quartic integrals, I don't think so, because if the interaction becomes quartic, suppose in a harmonic chain, you have xi minus xi plus 1 square. That's the interaction in the potential. Suppose instead of the square, you have fourth power. It's a steeper spring, that means much harder spring, nonlinear spring. If you have a nonlinear spring, then your Gaussian integrals becomes e to the minus constant times x1 minus x2 to the power 4, and so on and so forth. The moment it becomes a 4, the Gaussian structure breaks down. And you start getting elliptic integrals. And look them up, you'll get ratios of elliptic integrals. Now, whether the same trick can be done for ratios of elliptic integrals, I don't know. So this may not be extendable to various even powers. Just quadratic power is where it works. Anyway, I just wanted you to think about it. We have actually tried that problem. We did write a paper on this problem, but we didn't have such a complicated many-body system. It was a little bit more manageable with our system, which had 2 or 3 or 4 or 5 particles, and you can actually do it. But this is a more complicated system. Anyway, so you can calculate this, finally end up finishing this F3 square calculation. You can again get a simple delta, not so simple for F3 square. And then you can go to This is the paper. I think I sent you guys this paper. This is a paper where he reported this study. This was in 2013. This full study of alternating masses and the impurity. And this is the sort of the end, one of the main parts of the paper that I extracted, where he gives the where he gives the structures we discussed. In this case, because there are alternating masses, instead of 2 lambda all the way to 1, you have lambdas popping up, sets of 2 lambdas popping up alternately, 1, 1, lambda, lambda, 1, 1, lambda, lambda, goes on to infinity. And again, the continued fraction is summable, and you get this structure. And as I pointed out last time, the structure is a complicated structure. This is the point. What was I going to say? What I was going. Wait a minute. What am I doing? Sorry. How did it? What did I mess up? Here. This is the structure that I was saying. And this is the structure that has those branch cut dimensions. And it was managing those branch cuts that was needed to be able to get the calculation right. And the source of error that came in the literature came from not being able to manage this quantity correctly. That was the source of the error in the literature. Anyway, so if you calculate F4 involves momenta, simple, no problem. F4 can be done. So delta 4 calculation is easy. F5 is going to be the next challenge. But we have already seen how F5 is going to be done. That was the discussion I had about this transpose business and all that matrix. So this F5 calculation can be done. And beyond a point, you may not want to do it because you have already discovered the pattern. So you now keep repeating the pattern. Your calculation is done for all practical purposes. So F5 square has this factor L square. And that is what we checked, this L square piece here. And that's where I showed the formula. And if you do it with the formula, you end up getting what I showed you. And this is the factor J that enters from this kernel here. And you stick it in and you are done with F5 mod square. Anyway, I've already shown this to you. This is just another renormalization calculation. Coming finally to the same formula. And once you come to this formula, you go through the remainder of the branch cut calculation that he has outlined here. Unfortunately, while you can get the exact results, a lot of times these exact results, when things get this complicated, are of limited utility, not of limited value per se, but of limited use. Why? Because these exact results themselves are very complicated. And so for you to be able to understand what the exact result means, unless you make a nice plot of it, you really don't get a feel for it. It's not like a Gaussian or a Bessel function, or something along those lines. It's actually a whole bunch of series of functions that come in, and that's when things get a little messy. So, for example, when I give you these formulas, I'm embarrassed to say it doesn't mean very much. Just because you can write it down doesn't mean it's very helpful. So here, for example, this acoustic branch can be written, the acoustic is the sloshing mode, basically. And the optic is the going like this mode. So you have the acoustic, which is lower, you have the acoustic, which is the lower frequency, and then the optic, which is higher frequency. You're compressing the spring, frequency goes up. So the acoustic branch that comes in, phi acoustics, this is the phi, has this structure. And so therefore the A0 has this very complicated structure. But these B's are these guys here. So what are you going to make out of it? I mean, as far as my humble knowledge is concerned, this is not useful. Um, it is correct. It satisfies the initial conditions and everything. And if you want to look at the optic one, which is the optic one that you calculate. Oh, I lost Vivek. Let's see. There he is.
It's okay if I don't understand this slide at all.
Yes,
Okay.
it's perfectly fine if you don't understand this slide at all.
Okay, because I was looking at these slides before the lecture today and I understood everything up until the branch cuts. And then,
That's not-
or at least I understood where the calculations were coming from. I haven't done them myself. They seem quite difficult, but
yeah,
they at least were followable.
yes.
Okay.
I think that is a very important point. Many of these calculations, um, especially with this particular system, they are followable. The integrals you can do, Gaussian integrals you can do. Even the factor I showed you, that you can do. This L square factor or whatever. But this part, don't waste time on it. I just put it up so you have it in front of your eyes. You can take a look at it if you have questions. But for the life of me, I don't worry about this. So okay. So now let us try to get past this problem, get past this pristine harmonic oscillator chain, all same masses, single impurity, and the alternating masses plus impurity, just alternating masses. All of them have the same structure. All of them they have the same character. But let us now move beyond that. And this is a part that I'm going to not get beyond knee deep right now, because I want to come back to this whole story and build on it in April. But it's a fantastic sort of point in time to introduce it. All through the time when experimental tools were developing to study solids, experimentalists knew something very clearly. They knew that when you look at the frequency peaks, let's say of a certain solid experimentally, in the structure factor, dynamic structure factor, or in some other equivalent quantity, the peaks often are not very sharp. They can be quite rounded. Again, these are peaks associated with frequencies in the solid. In a liquid, you can understand that. In a solid, why would the peaks get rounded or rounded beyond a point? That was a question that was in the minds of experimentalists throughout time. So rounded in part because they figured surely it's not perfect springs that you have in the system. Surely you have nonlinear effects, and those are the ones that contribute to this roundedness, or rather broadening of the peaks. It's called peak broadening, also called peak softening, standard terms that are used in condensed matter. So Fermi wanted to check it and make sure. I mean, you have to understand the kind of scientist Fermi was from what I have read and heard. Fermi spent much of his life doing nuclear physics, but he had done almost every field of physics. And Fermi was one of those unique characters was not only an excellent theorist, but he was also a God-given experimentalist. Okay, so he was both. He was pretty much a whole package. So Fermi figured that, well, I want to make sure that this is okay, that nonlinear effects give us this rounding. So at that time, Los Alamos had this big machine, supercomputer that had come, this Maniac 1 machine. The year was 1954. And so Fermi asked his colleagues in Los Alamos, where he had an appointment, in addition to his home base, which was University of Chicago, to take on this study. And his cohort was this John Pasta and Stanislaw Ulam. They were both mathematicians. Ulam, in particular, was a very well-known mathematician, actually. And there was Mary Singhu, who was the lady who was actually running all the codes on Maniac 1. She was an expert programmer. She was not really a physicist or a PhD physicist. So the idea was that Fermi suggested, why don't you do something? Why don't you take a harmonic oscillator chain and just throw in a weak nonlinear term? Very important, weak nonlinear term. So then they decided that they were going to do the study. And so, by the way, this is X1 double dot and this is X1 double dot. Original paper had this typo. The double dot was missing. So X1 double dot, X1 double dot. The Newton's equation. And they figured that taking 64 particles was a good number. 2 to the power, that's why it's 64, 2 to the power, whatever it is. And then weak nonlinearity. So this is the harmonic term. The first bracket on the right side is the harmonic term in both cases. And the second bracket on the right side would be the nonlinear term. So this term, the alpha term as it's called, the alpha term is tied to cubic nonlinearity because this is the equation of motion. So therefore the potential would be cubic. And the beta term is tied to quartic nonlinearity. So cubic nonlinearity, quartic. And they decided that they were going to study these two systems. So Fermi, Pasta, Ulam, and Singhu embarked on this study. They embarked on this study sometime around summer or before summer of 1954. But as the results were beginning to become available, Fermi was diagnosed with stomach cancer. And so Fermi died shortly after that. He didn't live very long once the diagnosis was there. Stomach cancer is a very aggressive form of cancer typically. And he died in December of 54, if I recall correctly, end of November or early December of 54, Fermi passed away. But the results were becoming very interesting. And so Pasta, Ulam, and Singhu, they did not want this study to get lost. But in the absence of Fermi at the time, they couldn't really decide what to do with the paper. I mean, should we have Fermi's name? Or, we couldn't get Fermi to check it. What would he think? There are all these factors that come up when somebody passes away who was part of a study, who was the main force of the study, let's say. So in 1955, summer of 55, they put Fermi's name first. They didn't put in Singhu's name, but it was actually in the report. Fermi, Pasta, and Ulam were the main scientists, and they wrote this report, and they never published it, actually. So this was an unpublished Los Alamos report. That's why it's called Document LA 1940. And it was given this rather broad title, Studies of Nonlinear Problems, because they didn't understand the result. That was also one reason why, here, see, they say, the last few examples were calculated in 1955 after the untimely death of Professor Enrico Fermi in November 1954. The calculations were continued in Los Alamos. So I'm not going to go into the much in the paper. There's no need for it. There are 64 particles, so there are 64. If you turn off the nonlinear terms, there are 64 modes, right? 64 normal modes. And of those 64 normal modes, they excited the first 8 or 10 normal modes. And they had a goal. The goal was to see if these modes start to come together and mix, thereby leading to frequencies that are like beating patterns and so on and so forth. That was their goal, objective. Which led to these plots, these famous plots. This is for the alpha problem, meaning the cubic problem. So alpha value was set to 1/4. Remember, k was 1. So it was a weak nonlinearity. This is the integration time step 1/8. And the number of particles used here is 32. So there are 32 modes. And they excited the first 5 modes, as you can see. 1, 2, 3, 4, 5. And you see the first mode comes back almost unscathed after about 28,000 cycles, which is a long time in this case. The second mode here came back here. Second mode came back here. Third mode. Or third mode, you see this one. Third mode. And then has not come back yet. Fourth mode here again. Fifth mode comes back many times. These are the things they were seeing. And no matter what they tried, they kept on getting same kind of behavior. Very puzzling behavior. And then they looked at the beta problem. So this is the beta problem. And here alpha is equal to 1. I think this is a misprint. Alpha is equal to 0. Beta is turned on. And here also you see the same kind of physics. 2 repeats. 2, 2, 3, 3. No more 3 for a while. Weird patterns they were getting. Yeah.
I totally understand what we're seeing here.
What you are seeing here is that the energy is being plotted along the vertical axis and time is along the x-axis.
Mhm.
So this is the first mode that was excited. Energy in the first mode. So at t equal to 0, you see they have excited the first mode, the second mode, the third mode, the fourth mode, fifth mode. All of them are excited. See them taking off. Normally what would happen is these modes will start to mix. So very soon you will see that they are getting all kinds of mixed up beating patterns. And that is happening because of nonlinearity. That was the expectation. Here the nonlinearity is not that weak. It is still quite significant. But in spite of significant nonlinearity, you are running this system for very, very long times. Not short times, very long times. But in spite of running them for very long times, you are not able to have the modes start to mix with each other. Because if the modes retain their identity, then clearly the modes are very much there. It's just that they are essentially going through unscathed. You see, if you look at the dynamics of the system where modes are excited, you are sitting at one particle. Here we are not talking about particle. Here we're talking about the energy. But if you're sitting at one particle, let's say particle 10 out of 64 particles, then particle 10 will experience all the 64 modes in space and time. Because the mode is moving through. Each of these modes is moving through. So each particle experiences all the modes. Okay. So this is the system energy being distributed in the various modes. That's what you're seeing. If you go back a little bit, you see the energy and the mode distribution is here in equation 5a. Kinetic plus potential energy is half ak squared plus 2 ak squared sine squared pi k over 8. K is the mode number. So naturally, not all of them have the same periods, which is what you're seeing. The modes are mixing, by the way. Actually, the modes are mixing, but they're mixing so slowly that you don't see much of an effect. All you see are just that the energy versus time shapes are changing a tad bit somewhere, and sometimes not even changing. I mean, look at this 5, for example. Here, the 5 is so much sharper the first time it comes around 6,000 cycles. But when 5 comes around, no, 3,000 cycles, I'm so sorry, 3,000 cycles. When 5 comes around 6,000 cycles, even the shape of how the mode energy versus time traces is different. This one is asymmetric, this one is more symmetric. This is also a little bit asymmetric. This is also a little. So you see, all of these things are happening. There is some exchange going on, but not a whole lot, nothing dramatic. And this is the reason why they were very confused as to what is really happening. And they really didn't offer much of an explanation in the paper. And maybe this is one reason why this paper was never submitted for publication, because they didn't have the privilege to know what Fermi would have said. So they wanted to leave it as a report. And by the way, intriguingly, John Pasta, Stanislaw Lam did not really work on this problem after Fermi's passing and after this report to any significant extent. They did their own work. This particular problem, they didn't go back and beat on it. Singu did much later, but they didn't beat on it. So the next action came 10 years later. Zabusky is still alive in his 90s. Norman Zabusky was a professor at Rutgers for much of his life. This was before that, when he was in Bell Labs. And Martin Kruskal was a professor at Princeton Physics. So Zabusky and Kruskal wrote this very interesting paper, Interaction of Solitons. They introduced the word solitons in physics for the first time, although solitons have been known in mathematics, in a collisionless plasma, which is basically form of the Hamiltonian, and the recurrence of initial states. This is the recurrence of initial states. But if you read this paper, it is non-trivial. So let me kind of give you the point of this paper. Point of this paper is they took this model, the first model, alpha model. They took this model, which is a discrete equation in a one-dimensional lattice, and made it into a continuum equation. They basically assumed a long wavelength approximation. They said the particles are very close to each other, so close to each other that the particle dynamics adjacent to each other can be seen, can be connected by Taylor expansion. And so they managed to replace the discrete lattice equation with a continuum equation. And this is the form of the continuum equation they managed to pull out. And this equation has a long history. This equation was first solved in 1895 by these two gentlemen, Korteweg and de Vries. And by the way, they didn't pull it out of thin air. This equation had evolved basically from the 1700s. So from the 1700s, actually late 1600s, Newton was one of the first folks to get into this problem. Around 1700s, the European seafarers were trying to come to various parts of the world to colonize. Unfortunately, they were not getting very lucky with their ocean voyages. The ocean voyages had become quite dangerous. They realized that mid-Atlantic was much rougher than they had thought it would be, because Mediterranean is not that rough. But once you start to cross the Atlantic, things get different. In fact, for example, the southern tip of Africa, is it Cape of Good Hope? I forget about the cape there at the bottom. That part is very bad. In fact, it's very rough seas in that part of South Africa as it faces the Southern Ocean, the Southern Indian Ocean. And once you get past that part, as you get into the Indian Ocean, the area which is still adjacent to South Africa, that part of the Indian Ocean is a major ship sinker because it is majorly known for very large and dangerous and unpredictable waves. In fact, there is a current there called the Agulhas current, Agulhas. You can Google it up, Agulhas current. And the Agulhas current is a very dangerous current, creating large waves. They used to lose ships there. They also lost a lot of ships trying to cross the Atlantic because knowingly or otherwise, they were trying to come to the Americas. So there are various kings and queens who were trying to colonize. They got very worried. They said, well, we can't be losing ships and sailors like this. How the hell are we going to colonize? So they decided that they were going to get the mathematicians and the physicists involved to solve this problem of why the ships are sinking. And so naturally, the physicists and mathematicians saw this as an excellent excuse for studying waves, in particular nonlinear waves. So Newton was one of the first guns, but there's a very long list of everybody you can think of. There is Airy's function you may have seen in electrodynamics. Airy was involved, Fourier was involved, Bernoulli was involved. Then this guy Taylor was involved, Taylor Couette instability. All these characters from Europe who were physicists and mathematicians, they got involved. And that's how the journey of studying nonlinear equations began. And the culmination of that effort was the first exact solution created by Korteweg and de Vries in 1895. So from 1690s to 1890s, for 200 bloody years, this is what they were doing. So it was a big deal. It was a very big deal that 10 years after this work, historically, oh, here I was. 10 years after this work, after the Fermi-Pastel-Lamsingu work, Zabruski and Kruskal comes along and points out, hey guys, this is somewhat similar to this Korteweg-de Vries problem, isn't it? Fermi was long gone, but this turned on the interest of physicists to these nonlinear equations in a very big way. Before that, only Russians were worried about these problems. Now the Americans got worried about it too. Okay. So, but the problem was that this equation just produced solitons. By the way, this equation is a very active equation on which work is still done because it's super simple to actually get the result of this equation in your bathtub almost. So if you have a long bathtub, let's say, where the depth of the bathtub is very small compared to the length of the bathtub. Suppose you have a bathtub that's 100 feet long and suppose it's 3 feet deep. If you now push the water at one end of it, you will find that the water develops into a single traveling pulse eventually. It has to be narrow, it has to be shallow, and it has to be long. And this is the reason why this quarter-wave soliton was first observed by this British engineer called J. Scott Russell. Scott Russell was riding along a channel that came from the Firth of Forth into Edinburgh. So if you have, I don't know if you have been to Edinburgh, I have, and you can basically see if you get up to any height in Edinburgh, it's pretty flat. There are rolling hills. You see the Firth of Forth around there. The Firth of Forth is basically the part of Edinburgh that empties into the North Atlantic Ocean. It's like a jaggedy coastline, and that area is called the Firth of Forth. So Firth of Forth has obviously, there are inlets inside that are connected to Firth of Forth. So this Scott Russell was hanging out there, I don't know doing what. He was an engineer, and he saw that as a wave came in from the Firth of Forth into this channel, which was a shallow channel, it was not a deep channel, there was a wave that formed, which was like a single pulse wave. And that was moving at a steady speed, and he expected it to dissipate away. And it didn't. So that intrigued him, and he was following it along horse riding. And he followed it for a long, long way. And this wave went in and in and in and in. So he first reported it in a Royal Society report in 1838. Now, he was not really a scholar. He was an engineer who wrote a paper. And of course, all the snobs at Royal Society said, what kind of crap is this? First of all, whether we should even dignify our pages by printing this. And then some people felt, well, it's an observation by an engineer. How can you say it's bullshit? So it was published as a Royal Society report, not a scientific paper per se. And then in 1845, he wrote another paper saying that, hey guys, I told you this, I've seen it again. There's a phenomenon here. You should do something about it. You should investigate this. So 1845 is when it was more or less rubbed into the Royal Society people that, look, there is something going on. You guys have no clue. So 50 years later, in 1895, Orteweg and De Vries constructed this equation, which was a simplified, chopped off, mangled version of the original equation that Newton and all these guys were studying. And the equation looked like this. So it became known as the Orteweg-De Vries equation. So now what happens is they solve this equation with the Orteweg-De Vries soliton, just a pulse that propagates, fixed speed, and point out that, look, your Fermi-Pascal system must have this guy. But why that would produce recurrence of the modes was not obvious. So that's why I'm telling you that the reason why it would put recurrence of the modes is because, first of all, you have a system, if you turn off the nonlinear term, which has modes. So if there is no nonlinear term, these modes will never go away. If there is no dissipation, the modes will remain forever. If you now add this nonlinear term, what do you expect? You expect the modes to mix. That's what Fermi expected. Well, the modes are mixing, excepting the time scale of mixing is very long. Very, 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 very long. may even be longer than the age of the universe. That's the time scale of mixing is so slow. So, and the reason why the mixing is happening is because the underlying dynamics of the system involves some soliton type behavior. How soliton type behavior, why soliton type behavior, how would it look like in real life, in real time? People didn't really understand. And honestly, people still don't understand very well. I can tell you my understanding. And that will be quite inconsistent with what Korteweg-Dubry's equation on its face shows you. Suppose you have a harmonic oscillator chain, masses and springs. The springs are harmonic plus a little bit of nonlinearity. This is one of the hardest regimes, by the way, in which you can study the system. So now what you do is you, let's say, instead of exciting modes, you push a mass with a velocity at t equal to 0. Start your stopwatch. So you've given a system which had no energy, just the masses and springs unstretched. You have given the system an initial kinetic energy perturbation, right? Just pushed it, that's it. So now what will happen? This kinetic energy will get partly converted to potential energy and the remainder kinetic energy, because the spring will get compressed a little bit. So here you have a mass, here you have two nearest neighbors, you've given this a kick. So this spring got slightly squeezed, this spring got slightly dilated as the other one got squeezed. So this has some kinetic energy and some potential energy. Virial theorem tells you how much is kinetic, how much is potential. In fact, this is what virial theorem does. You take a system, virial theorem tells you how much is kinetic, how much is potential. Just the initial energy given, just the interactions themselves point out what it is. It's not always easy to calculate. In this case, it's not easy to calculate, but this is what happens. So now this energy will start to flow on the right as a compression pulse and on the left as a dilation pulse. Meaning, spring dilation will move to the left, spring compression will move to the right. If you now go to a mass, let's say 10 masses or 20 masses away from the original mass that you kicked, and you put an accelerometer inside that mass, and you record what is happening to that mass, you will find that the mass first moves like this and back. This and back is your solitary wave pulse going through. Then it starts to oscillate. And it will oscillate for a long time. And that is the tail of the solitary wave that is from harmonic oscillations. So you have a nonlinear piece that's coming from the nonlinear term, and you have a long tail that is from the harmonic oscillations. Do you see a tail in KdV equation? No, there is no tail in KdV equation. And that is the shortcoming of this study that led to further confusion, because Sabuski and Kruskal pointed out there's a soliton aspect to this problem, and they were 100% correct. But because they studied the nonlinear problem using an analytic approximation, they dropped terms, and those terms would have given them the oscillations had they remained. But it makes the problem unsolvable, so they dropped it. So in real life, you have a soliton pulse in the front, and you have this long oscillatory tail. This is the reason why solving weakly nonlinear equations are difficult, because you always have this overwhelming oscillatory tail. And it is because of this bloody oscillatory tail that you have such slow mode mixing. Because the soliton energy is very weak, the oscillatory tail energy is very long. The soliton energy is very weak because the alpha is very weak. The coupling of the nonlinear piece of the spring is very weak. That's the point. That you won't find in Korteweg-Dubry's paper. So this is your alpha FPU problem, equation 1. And if you now do this approximation that yn of t is yn h is the interparticle distance of t, then n plus 1 and n minus 1 can come as a Taylor expansion. This is the way it is done. So now this Taylor expansion that you have, this Taylor expansion enters into the first term on the right side and also into the second term on the right side. So now you have a little bit of a messy situation on the right. And if you simplify that, you get this version of a second order equation. You see, this first term on the left and the first term on the right is a wave equation. You see that? That's a wave equation. Double derivative in time, double derivative in space. And then you have this fourth derivative in time, fourth derivative in space, and the double and single derivative in space coming in with a cubic coupling. This comes with a quartic coupling. Now there is another step after this. And this step is that you introduce the strain variable u, which is dy dx, strain variable. And in terms of the strain variable, you rewrite the equation and you have this structure that you had. And then you introduce a co-moving frame of reference because the soliton is moving at a constant speed. So you introduce this co-moving frame of reference, meaning that space and time get related by speed, which is exactly what this term here does, x minus ct. Space and time are related by speed because the thing is moving at uniform speed. So the moment you do that and the moment you rescale time, this is just for beauty, no real major physics, and do the correct transformations, you write it in terms of xc and tau, and you get this structure. And this structure actually is the KdV structure. With slight decoration, you come up with this KdV structure. So the KdV equation is a continuum version of your alpha equation. Plain and simple. And what is the solution? The solution is a bump. The bump. This bump is moving. This bump is your soliton. And the function that solves this soliton, solves this equation, is the Sech square function. So for all soliton solitary wave, I'll tell you the difference. This is what you have. You have the Sech square solution. So the original wave that you would have, this oscillatory wave, has now become this. Actually, like I said, this is just the front end of it, because this moves faster than the wave which is slowly dispersing. So this is the front end of it, and then there's a long wagging tail, the oscillatory tail, which you don't have here. You don't have here because this is the limitation of the treatment. It has nothing to do with correct physics. The physics is not given correctly, but the soliton is captured correctly. That's what is shown. In fact, in this picture, this is space and this is time. This direction is time, this is space. So you can see there are two solitons coming from earlier time to late time. This soliton and this soliton, they meet around here in the middle. And they slow down ever so slightly and then resumes unscathed. And this guy also slows down ever so slightly and resumes unscathed. They pass through each other. And if they pass through each other without scattering, excepting for a momentary slowing down, without scattering, then they are called solitons. If they scatter, they are called solitary waves. That is the difference between them. So when somebody is describing a soliton, there is no scattering. Almost always, if not absolutely always, it comes from an integrable equation, which you can directly integrate out. If there is scattering, that comes from a non-integrable equation, which you cannot integrate because of scattering. So, question now becomes, is the Fermi-Pasta-Ulam-Singu system an integrable system? That's why Zabusky and Kruskal found the soliton. The answer is no. It is not a non-integrable system. It's not an integrable system. It is a non-integrable system. It is far more complicated than what Zabusky and Kruskal took it to be. Their great contribution was pointing out, hey, there are solitons here. What we learned much later was there are solitary waves there. It's even more complicated. And then there are these long oscillatory tails from the harmonic term, which they didn't worry about in their study, at least not carefully. Couldn't. So the story of nonlinear waves, the story of nonlinearity begins here. In fact, that Fermi-Pasta-Ulam-Singu paper is called the first paper of the new field of experimental mathematics, because it's an area of mathematics, area of physics that you cannot study analytically anymore. Our analysis is simply not as advanced. So you have to study it numerically. And hence, numerically experimental mathematics. So, as you can see, the idea of influence of nonlinearity in the context of a lattice is a perturbation problem. But the role of nonlinearity, when you remove the context of a lattice, mostly, becomes an existential problem. They are very different systems. So that's why I said I want to cover that. So this is everything I told you is kind of summarized here in this slide about the velocity perturbation and so on, but I told you in more detail. I can't do this here, so I'm going to stop here now. But I want to finish up our discussion of the generalized Langevin equation, but the case that we had not studied, which was a non-Hermitian system. So I want to do a small discussion on Thursday of the non-Hermitian system problem. And basically, you will see that in the non-Hermitian system, our original structure of recurrence relations will have to be extended a little bit. And in doing that, we'll connect back with the theory which we didn't do, which is Mori's original theory. Because Mori's original theory gave us the whole gig. We did the Hermitian system. Well, people study Hermitian systems only, but with Hermitian operator as our starting point. And we have now learned a little bit of it. Now it becomes a non-Hermitian operator as a starting point. And so that they can be extended. Okay, let's finish here, and we will carry on Thursday with an extension of this. What we will do is I'll give you the charge now of, after we are done with this part, of doing a thorough study on memory functions. So we'll study the memory functions of all the systems we have studied. That's what you will do. That's your project now. And see how these memory functions shape up. That way you'll get to do some calculations, do some continued fraction work, read the papers, study the deltas, get your hands dirty in doing some secondary analysis of what all you have done. And who knows, if we find something interesting, it might allow us to write a little report up as well. Okay? Good. Any questions? Okay. So keep your
Not yet.
Okay, keep your questions popping. We'll address them on Thursday. All right. Take care.
Thank you.
Bye-bye.
Yeah.
Thank
Yeah.
you.
Good night.
Good night. Let's see now. I've lost my thing. Okay, stop here. Stop recording and